in Algebra 2 or Algebra 3, so we have some ideas about exponential and logarithmic functions. Today in Notes 3.1, we're going to be talking about exponential functions and their graphs. Tomorrow, we'll do 3.2, which is logarithmic functions and their graphs. So we're kind of focusing on our graphing here at the beginning of the chapter. Now, before we get into the graphing, you have copied down something called the one-to-one property. You actually probably used this property last year in Algebra 2 when you were solving equations. You just maybe didn't call it the one-to-one property. You just kind of learned what to do in an equation if there are two exponents. So the one-to-one property says basically this. If you have a to the x set equal to a to the y, the only way those things will ever be equal if they both have base a is if they have the same exponent. So we say that's true if and only if x is equal to y, the exponents are equal. Okay. So if you have an equation where you have exponent on the left and exponent on the right, what you would like to do is have the same base so that you can apply the one-to-one property and say that the exponents are equal to each other. So here's my example. 2 to the 2x minus 5 equals 8 to the x minus 3. Now, there is an exponent on both sides, but the trouble is we don't have the same base. So it may be your job, in order to be able to use one-to-one property, to rewrite one or both sides in some cases so that they have the same base. Now you have to be really thoughtful here. You want to rewrite one of the numbers, but you don't want to change what it actually is. So you still want it to be 2 on the left. You still want it to be 8 on the right, but you want them to have the same base. So the question is, which one will you rewrite? 8. We will rewrite it as 2 cubed. Okay. So we can keep the base 2 on the left. 2 to the 2x minus 5 equals. We can change 8 to be 2 cubed. And as you look at your original problem to your first line, they read the same. 2 to the 2x minus 5 equals 8 to the x minus 3. 8 just now looks like 2 cubed. You can use your property of exponents right here, power of a power. What do you do with those exponents? Multiply them. So that's really 2 to the 2x minus 5 equals 2 to the 3x minus 9. So you got to distribute that 3. And then now we're set up to use our one-to-one property. We now have the same base, two things raised to exponents. That's only true if the exponents are equal to each other, x equals y. So we can say 2x minus 5 equals 3x minus 9. Now that's a really easy equation to solve. Subtract the 2x, add 9, x equals 4. Now, if you were uncertain as to whether or not you rewrote that correctly, if you had changed the equation, if you were getting a little confused on a quiz or a test, what could you do to check your answer? Plug that x equals 4 back in. So if I scroll up to the top here, if I were to plug 4 into the left, 2 times 4 is 8 minus 5, so that would be 3. 2 cubed is 8 on the left. And then on the right, I would have 8 to the 4 minus 3, which is 8 to the first. That's equal to 8. So then the two sides are both 8. So I knew I did it correctly. Okay, now we're going to move on to actual exponential functions work and their graphs. First, we're going to define the exponential function. Now this may be slightly different if you're looking in your Algebra 2 notebook. I think the Algebra 2 textbook is going to use like a b to the x, which makes sense when they use that because b is a base. But our pre-calculus textbook uses a to the x. A is the base. And then there are a few things to know about exponential functions a to the x. The first one is that a is greater than 0. That means that your bases have to be positive They can't be equal to 0. You can't have negative bases. If you were to have a negative base, like negative a raised to the x, think about what would happen if you use different types of exponents. When it's odd, it's going to be a negative answer. When you switch to the even, it's going to be a positive answer. And if you were trying to graph that, your graph would just be like a zigzag up and down, which is not an exponential function. So this is not okay. You can't have a negative a to the x. Now you can put a negative a in front. This is really just a reflection. Okay? So you would reflect all your y values, but your a would still be a positive number. All right, and also a cannot equal 1. Think about 1 to the x. It's a pretty boring function, right? It's really just a constant function. So a has to be basically a number between 0 and 1 or a number greater than 1. Okay, those are the possibilities. And then finally, what makes something really an exponential function is the variables in the exponent. So we're looking at things like 3 to the x versus the things we saw in the last chapter. They maybe had exponents, but this was a polynomial. The variable is the base. Okay, so that's not exponential, x to the third. That's polynomial. We're looking at things like 3 to the x. So you can identify it as an exponential function because the variable is in the exponent. Now we're going to look at some graphs. I'm going to start with 2 that are just like basic graphs, and then we'll do one that is it's got more stuff happening in its equation. Okay, and we'll look at how we can go ahead and do that. So here's my first one. F of x equals 2 to the x. Exponential. Now, in terms of exponential functions, there's a family for every base. So like there's a family for all the 2 to the x graphs. They all come from this guy. This would be like their parent graph. And then there's a new family for 3 to the x. They all base themselves off of 3 to the x. And that would be true for any new base value. Okay, so I always focus on like what my base is when I'm graphing. We're going to make a table of values. You may already kind of know what shape this is going to be, but we're just going to look at why these graphs look the way they do here at the beginning, and then we'll kind of like take the shortcut route going forward. So I usually pick some negative, some positive, 0, and I put them in my table. Now we'll have to do a little review here. When we do 2 to the x, and we put in a negative, anybody remember what negative exponents do, Elena? No, that's a fraction exponent. I think you're thinking, oh wait, tell me more, you put it in the denominator. Yeah, so I often say like negative exponents flip what they touch. Okay, so let's do, Campbell was talking about 2 to the negative 1. That's really 1 over 2 to the first. So she's saying put it in the denominator and make it positive. And then that's 1/2. Okay. So if I did 2 to the negative 2, that would be 1 over 2 squared, which is 1/4. What about 2 to the 0? Anything raised to the 0 is 1. 2 to the first is 2. 2 squared is 4. Now, I'm going to add to my table of values here. I'm going to put in a negative infinity and a positive infinity. So my table is going to be a little bit crowded there. I'm going to put in negative infinity and positive infinity. Okay, let's do the positive infinity first. If you do 2 to a positive infinity, which you really can't do because infinity is not a number, but if I just kept multiplying 2 by itself, what would happen to my number? Really big, right? Huge. Okay, so 2 to infinity is some huge number. Basically, infinity, right? It just keeps going. Does that make sense? Okay. What happens when I do 2 to the negative infinity? Okay, it's very, very small, so it's 1 over 2 to infinity, which we just said was huge. And 1 over a huge number is very, very small. She's using some good math words. I'm using just regular people talk, right? 1 over a huge number is almost 0. If I take a Snickers bar and cut it up into a million pieces and then offer you a piece of the Snickers bar, are you very pleased with me? No, you might not even see what I'm offering you. Okay? So essentially we could say at some point it's really 0, but theoretically in math it's never actually going to be 0, right? 1 over something is still something, not nothing. Okay? So when we're graphing, that means, and you may recall from your previous knowledge in Algebra 2, that means when we're graphing this, and I'm doing -2 1/4, -1 1/2, 0 1, 2 1 2, 2 4. As I go to negative infinity, I'm getting closer and closer to 0, but I'm never actually getting there. So I'm producing a horizontal asymptote. As I go to the right, notice my graph is just pointing upwards. It's just going to keep going towards positive infinity. So you'll probably want to start drawing your horizontal asymptote on your graphs. It's a pretty important characteristic of the exponential function so that you know what you should or should not cross. Okay. And then we could go through and we could label these things. So like domain, what things were I allowed to put into my function for x and get answers back out? Anything, right? I went from negative infinity to infinity. What kinds of things did I get out in the y column? Greater than zeros, but not equal to 0, right? So we're going to use parentheses 0 to infinity. So note that like for any exponential function, you're really not going to use brackets at all because you're never going to include your horizontal asymptote. Your horizontal asymptote would be at y equals 0 in this case, which is the x-axis. And the y-intercept I can calculate by plugging 0 in for x. It's also on my graph. That's the ordered pair 0, 1. And then if I asked you about this graph, is this graph increasing or decreasing? It's increasing over the whole domain, right? It never is decreasing. So we would say from negative infinity to infinity, we are increasing, and then maybe like not applicable or null set for decreasing. Okay, questions, concerns right there. Now, this is an example of something called exponential growth. And one thing that I want to point out right now is growth does not mean increasing. Although in this particular case, the graph is increasing from left to right, and it does represent exponential growth. Imagine if we were to reflect this graph over the x-axis, if we put a negative in the front, -2 to the x, then my graph would look something like this. There's y equals -2 to the x, and that's still growth. Okay. So one thing we want to point out about exponential growth is it's talking about the rate of change. So as I move to the right, as x increases, the rate of change, or the slope between 2 points, is increasing faster and faster. And when the slope between my 2 points increases faster and faster, I move away from my asymptote. Okay, so those are both examples of growth. The other one that we want to look at are going to be decay functions. Okay. So my next function over here on the side is going to be f of x equals 2 to the negative x. Now, if you're raising it to the negative exponent, think about what we talked about. What's the base really? Instead of 2, the base is 1 over 2, the reciprocal of that, because we would flip what we touch. So you could also think about this like this is f of x equals 1/2 to the x, which is going to end up being a decay function. Okay, so I'm going to put in like -2, -1, 0, 1, and 2. When I put in the negatives, those things are actually going to become positives in my original function. 2 to the negative, -2 is really 2 to the 2, which is 4, 2, 1. And then when I drop in my positive exponents, they're going to be made negative, so I'm going to be doing my flip. So I'm going to have 1/2 and 1/4. So notice the changes, instead of like moving away from the asymptote as I go to the right, now I'm moving towards my asymptote. I'm getting closer and closer to my asymptote. Okay, so here's my horizontal asymptote. And like I said, this is an example of decay. So in this particular example, you would see that decay does look like a decrease. But if you were to flip it, decay can actually be increasing as well. Okay. So again, decay and growth don't have anything to do with increasing or decreasing. Okay. If I were to flip this, this would be y equals -2 to the negative x. That's still decay. Now we could answer those same questions about domain and range, horizontal asymptote, etc. So the domain is still -∞ to infinity. Range, I'm doing the black graph, is 0 to infinity. Horizontal asymptote still y equals 0. Y-intercept still 0, 1. This time there was no increasing, it was decreasing from left to right. Okay, so something that you maybe talked about in Algebra 2 is the difference between growth and decay is really based on the value of the base, so our A value. If A is greater than 1, it's an example of growth. If B is less than 1, it's an example of decay. But notice, if you have a negative exponent, then it would be greater than 1. So if you have a negative exponent and an A value greater than 1, it's actually decay. Questions or concerns so far? Okay, so those are just like basic ones, just to kind of review like how the shapes work, growth and decay, what are the possibilities for your graph to look like. I mean, most of your graphs should look like one of those 4 graphs, moving away from the asymptote, moving towards the asymptote, above or below the horizontal asymptote. Okay, those are the 4 shapes. And then here's an example of a graph where there's more stuff happening. So I'm going to teach you how I would do this. So you're going to be doing this on the no calculator parts of your quizzes and tests. So Friday's quiz is going to be half no calculator, half calculator. So you'll do one part, then the other. And we've got to be able to do this without a calculator. So I'm going to be graphing f of x equals 2 to the x plus 2 plus 1. Sometimes it can be tricky when you're just like making a table of values to just plug numbers in and first of all evaluate them exponentially, and then also make sure you have like a good section of your graph. You know how like when we're graphing quadratics and absolute values, you really want the part of your graph that has the vertex in it. If you don't have the vertex, it doesn't look like a parabola or a V. So the same is true for the exponential function. We really kind of want that little part, it's kind of like the corner or the curve, I call it the hook of my exponential function, where it sort of like takes off or it slows down. Okay, so you really kind of want to know where that point is. So in order to help me get that point, I actually make a table of values not for the function, but for its parent function. So in this case, this is 2 to the something, blah, blah, blah. I really just want to look at 2 to the x. If it were 3 to the something, then I would look at 3 to the x. Okay. And those are going to be really easy for me to evaluate, right? I might even just narrow it down to 3 numbers. -1, 0, and 1. That's going to be 1/2, 1, and 2. That doesn't take me but 5 seconds of math in my head without a calculator. Okay. And then I can go back up here. This x plus 2 and this plus 1, those are transformations. So they're like your a's, h's, and k's. So what is x plus 2 and the exponent doing to your graph? Moving it left 2. It's with the x, so it's like h. So we're going left 2 And what does the plus 1 in the back do? Up 1. Now, you may also want to make a note to yourself that any kind of vertical shift not only will you vertically shift your points up 1, but you should shift your horizontal asymptote up 1 as well. You won't notice the horizontal shift on the horizontal asymptote because it goes left and right forever, but you definitely need to move it up or down with your graph. So I'm just going to plot those points, -1, 1/2, 0, 1, 1, 2. Quick little sketches of them. And I would know, like, for any of these parent functions, 2 to the x, 3 to the x, 4 to the x, the horizontal asymptote would have been the x-axis, y equals 0. But now everything has to be moved left 2 and up 1. So left 2, up 1, left 2, up 1, left 2, up 1. And in addition, I'm going to move my horizontal asymptote up 1. Now, if you want to like lightly sketch the other graph, you can do that so that you can see, okay, it actually looks like I just took that graph and dragged it left 2 and up 1. Or like me, I just mark the points and then move them. Okay, so wherever you're comfortable there. I don't mind if there's 2 graphs, just make the first one light. Now, can you answer questions about domain, range, etc.? Sure. You'll have to be careful here. Remember, shifting may change some of these. So domain is still going to be -infinity to infinity. But the range is no longer 0 to infinity. It's now 1 to infinity. Okay, notice the range. I'm never using the brackets. I'm using the parentheses because it's not included. Okay. Horizontal asymptote is now y equals 1. So some people might write like a note to themselves in their notes. Your horizontal asymptote will always be your y equals k, whatever your vertical shift is. And then that means that k is the thing in the range as well. The y-intercept on this one, because I only did 3 points and I shifted them left 2, I don't actually have a y-intercept like that I found on my graph. So if I needed the y-intercept, I should actually go to the original at this point and plug 0 in for x. So that would be 2 squared plus 1, which is 5. Kind of missed-stitch across right there. That's okay. And then is this graph increasing or decreasing? Decreasing. Questions, concerns? Okay, so when you're practicing on your homework tonight, I would try to graph like the parent function, 2 to the x, 3 to the x, 4 to the x. Those are really easy tables for you to make without a calculator. And then use your shifting. That's probably the best way. And notice I'm shifting that interesting little piece of the graph that I want, where it's taking off or where it would be slowing down. Okay, so that's kind of like an interesting part of your graph that you would want. If you only did -1 to 1 on this, you'd get this like really straight part, which wouldn't be as interesting. Okay, next up we're going to talk about some calculator problems. And this involves the natural base. So if you could get out your graphing calculator, we're going to look at that. If you need to borrow a graphing calculator for class, I've got only a couple. So then share with the people around you. Got one more up here if anybody needs one. Okay, the natural base is the number e. Does anybody remember the value of e? Approximately 2.718. That's our value for e. And e is generated by our compound interest formula, which we're actually going to cover on the next slide. So it's called the natural base because it represents what happens in nature. I often say, like, think about you as an individual. You're growing. You're still young. So over the course of 1 year, you're growing all the time, as opposed to your body's just like storing stuff up, and then on the night of your 16th birthday, you magically like grow 1.5 inches or whatever happens, right? That's not how it works. Okay, so it's not working on a schedule. It's all the time. That's why we use the number E. Same thing for like your cells dividing in your body. That isn't happening on a schedule. It's not like at midnight every night the cells divide. Okay, it's just always happening. So E represents that, the things that happen in nature where it's happening all the time. And since E is irrational, we're going to use our calculators. We're going to graph f of x equals e to the x. I'm going to show you a cool feature on your graphing calculators if you don't already know about tables on your graphing calculators. So get your graphing calculator. Gotta find mine. Oh, there it is. And go to your y equals menu. And if you want to graph a function, you can type it, like you can type in your function, and then you could hit graph to see what it looks like. Remember, to get E, you have to type second natural log, and it'll bring up an E. And then you have to put X in there for your exponent. You want graph E to the X. X is next to your alpha button. Okay, instead of hitting graph, though, if you just type second and then graph, because above it says table, it will take you to a screen like this. And you now have a table of values. You can scroll up and down and see what the values of e to the x are. So if this is on a graphing or a calculator portion of your exam, you could just type in the whole e function, whatever that may be, and then you could go to the table, and instead of like manually plugging in -1, 0, 1, 2 to get your points, you could just pull your points from your graphing calculator. Okay? And I would be okay with that. And just make sure you type in your function correctly then. So I'm going to make a list of some of those on my screen in a little bit. Notice if I were to scroll up on this, what's happening as I go towards -infinity to my value of y? It's basically getting really close to 0, right? Times 10 to the -9th. So it's like 0.000000. So it's going to have the same sort of characteristics as the other functions where it will have a horizontal asymptote at 0. So I'm maybe going to do like -1 was 0.37, 0 was 1, 1 was 2.78, and I think this one is like 7.38 if I put in 2. Okay, so then I can plot some of those points. -1.37, less than half, 0, 1, 1, 2.78, and 2, 7.38, something like that. So definitely if you're graphing an e function with a calculator, you're going to have decimals there. So just pick a few points, plot. You only need like the nearest tenth really in your table, because I'm not going to be that picky. 0.37 from 0.38. And then you can do all the other things, right? Domain, range, asymptote, those things still exist. Does anybody have any questions about that? Okay, so yay! On your test quiz on Friday, there will be some graphing calculator options, right? Finally, you use your calculator. Okay, I'm not going to go through those extra things, but you certainly can if you want. Next up, we want to talk about compound interest, another calculator problem. So there's two formulas for compound interest. Make sure you jot these down. A equals P times 1 plus R over N raised to the N times T. And A equals P times E to the R times T. Oops, that was like an N. R times T. Okay, remember in these equations, P is called your principal. That's your starting amount. R is your rate. N is, well, that's on that one. I'm going to put T here. T is time. Time is usually in years. this one has n, where PERT doesn't have n, so n is the number of times compounded per year. So do you remember problems where it would say like compounded annually? So then n was equal to 1, or compounded quarterly, so n was equal to 4, compound monthly, n equals 12, daily, n equals 365, and you plug those things in. Those are going to be problems that generally represent things that aren't happening in nature. They're things that can work on a schedule. So a lot of times financial work is done with a compounding schedule. Like you get a little bit of your interest or a fraction of your interest every month. It's compound monthly, so that then you earn money not on just your principal, but on a fraction of your interest that's been added to your account. So then you earn more money. PERT over here, you're going to look for the keywords compounded continuously. So remember, this has the natural base E in it, so it's representing what would happen in nature. Nature's not going to run on a schedule. Population doesn't reset every January 1st and everybody has their babies on the same day. It's happening always throughout the year, every day, every minute. So that's continuously. Okay, so a lot of times you'll see natural base or PERT formulas that represent things in the real world, okay, that would run on a continuous schedule. Okay. So I'm going to put up the next slide and I'm going to label the parts and put them into the formulas, but I'm going to let you guys work on calculating them, and you can check with your small groups to see if you get the right answers, and then I'm going to pass back your tests so that we have time to at least see those. So this is the day of a child's birth. A deposit of $500, so that's my P, is made in a trust with 2.25% annual interest. So that's going to be my R, and I have to change it into a decimal. R is 0.0225. Find the balance in the account on their 25th birthday, so that's 25 years later, so T equals 25. If the interest is compounded quarterly, so I'm going to put N equals 4. That would be the amount in my account is 500 times 1 plus 0.0225 divided by 4, raised to the 4 times 25, or you might cross that off and say 100. Okay, so remember that those things need to be multiplied either in a set of parentheses in your calculator, or you do it separately. And then this one will be 500 times e to the 0.0225 times 25. Okay, so while I'm handing back your tests, and I'm going to pick your tests back up, so don't pack them away. But while I'm handing those out, you can work on plugging those into your calculator and seeing if you get the right answer. Talk to your group members if you disagree, okay? You can just sit on my desk, Randy. Thank you. Okay, so can anybody give me the answer for A? I think it's 870, help me out, 0.15, okay, and then this one is 877 point, Everybody got that one for me? Nobody typed that into their calculator? $877.53. Okay, so if you're not getting these two answers, then you're typing something in incorrectly, and we want to kind of look for what that is. Okay, so just kind of be aware of that. If you want to jot down what the correct answers are in your notebook, you could do that.